The mean, median, or mode can describe a representative data value around which the others congregate. In other words, they can tell us what a typical data value might be, but they don't give us any information about how spread out our data is or how near our data points really are to that median or that mean. So for that, there are a couple of ways to characterize how spread out our data is. The simplest way is to use the range, and this is just the difference between the largest and the smallest values. If we look at this example, find the smallest value in the table. I believe it is 0.2. And then look for the largest value. And I see a 1.3 in the second column. I do not see anything smaller, so this looks like the largest. And so my range then will be the difference between the largest and the smallest. So I take the 1.3, subtract the 0.2, and that gives me a range of 1.1. Now, when we have grouped data, we need to look at the smallest and largest possible data values. We do not know exactly where our data values are. We just know that they fall within certain intervals. But if I look at the smallest possible value, that would be 1.5, which is the lower boundary of the smallest class interval. The largest would be the upper boundary of the largest class interval. So my range will be the difference between these two. 13.5 minus 1.5, which is 12. Now, even range doesn't give us a lot of detail about our data sets. If we look at the data sets represented by these three histograms, and all of them, the mean is 10, which you could calculate as we've done before. The median, remember that is the data point so that half the data values are above it, half are below, and we know it'll be somewhere in the middle bar in each case. We don't know, of course, exactly where it is, but we'll put it in the center of the center bar, which would be at 10. And in each of these, the data range from 7.5 is the lowest possible data point, 12.5 is the largest. So we would subtract those to get the range of 5. In other words, we have 5 bars with 1 unit wide in all cases, and so our range is 5. So in all of these, our mean, median, and range are identical, but we have very different data sets. This one has a lot of data points at the ends, very low, very high, nothing in the middle. This, we say, has a small variance. It does not vary. I'm sorry, this would be a large variance because it does vary a lot. We have a lot out at the ends. This one would have a small variance because the data points are all congregated near the middle. They do not vary as much. Turns out variance goes along with something called standard deviation, which we will learn about. So if we have a large variance, that also means we have a large standard deviation. Deviation has to do with how far we are deviated from the mean, in this case, a long ways, because our data points are out at the ends. And in this one, we have a smaller standard deviation. So what are variance and standard deviation? Well, that's what we're going to learn next. Here's a formula for the sample variance. This will make more sense once we get to the example. What we're going to do is we're going to calculate the mean in the usual way. We will subtract the mean from each of our data points. That tells us how far they are deviated from the mean. And of course, if we just do that, those would be our deviations from the mean. Some will be negative, some will be positive. And it turns out if you averaged all those, you would get 0, and that would not be very helpful. What we're going to do is we're going to square them. We're going to square each of those. Then we are going to add them all up. And then we're going to divide by not the number of measurements, but which would be n, but rather n minus 1. The reason for that has to do with a concept called degrees of freedom. Those of you who take a statistics class will learn more about that eventually. Suffice it to say that that gives us, using n minus 1 for our denominator, gives us an accurate measurement when we have only a sample instead of the entire population. If we are trying to find out the variance for the entire population, we use a different symbol. Again, we're going to use Greek letters. In this case, sigma. This is the lowercase sigma. Greek letter sigma. And the formula is identical, except if we have the entire population, we do divide by n, the number of measurements. Let's do an example. Let's look at this data set. What we're going to do first is we're going to calculate the mean in the usual way. How do we do that? We add up all of our data points and divide by the number of data points that we have. We're going to assume it's a sample. So our x bar, we will add all these up. We will divide by 7 because that's how many we have, and you should end up with a mean of 69. Next, we want to calculate our variance. We're going to call this s squared. Again, we are going to use usual English letters for samples and reserve the Greek letters for when we have the entire population. So what we're going to do is, for each of these data points, we are going to subtract the mean and square it. And add them all up. Now, let's determine the variance. Okay, we're going to indicate that using English letters. Remember, those are for samples. We reserve the Greek letters for entire populations. This will be s squared. The way that we're going to determine it is we're going to take each of those data points, subtract the mean, and square. So 75 minus 69 squared, 16 minus 69 squared, 50 minus 69 squared. We're going to add them all up. Now, for our denominator, we are going to take the number of data points, subtract 1. So we have 7, but we're only going to use 6 then for our denominator. Punch all this into your calculator. And you should end up with 4464 divided by 6, which is 744. This is our variance. Now, let's move on to something called standard deviation. Notice we squared, when we subtracted the mean and we squared, we changed the units. In other words, if we would have started with inches, we will now have square inches. And so we are no longer in the same units as the original data points. The way we're going to take care of that is to take square roots. This is what we call the standard deviation. And you can think of deviation as meaning distance from the mean. Notice this is the same. The part underneath the square root is exactly what we had for variance. Remember, variance was s squared. Here we have s. We're only taking square root, the square root of what we had before. For samples, our denominator will be n minus 1. For populations, our denominator will be n. Let's do an example. Here they've told us it's a sample. Before we can find the standard deviation, we need the variance, and before we find that, what do we need? We need to find the mean. So that will be the very first thing that I will do, is to find the mean, which I will call x bar. So I add up my data points, divide by the number that I have. I have 7 of them. I should end up with about 7.714. Now, you do not want to get rounding error in your calculation of the variance and the standard deviation. So what you want to do is save this in your calculator. If you have a graphing calculator, there should be a store button on it, and you can store it in A or B or C or whatever letter you like. If you have a scientific calculator, you should have a memory recall in which this can be stored and then pulled up to be used again later. Now let's do the variance. So this is called s squared. We have a great big fraction here. What's our denominator of our fraction going to be? Not 7, but 7 minus 1. And actually, we're going to make this an approximately equal sign because we know we're having to approximate our mean. So each of our data points, I'm going to subtract the mean and square. Remember, whenever I write 7.714, that's not what I'm typing into my calculator, because I do not want to round until I get to the very end. Oops, I ran out of room. You know what? I'm going to place it right above here. And I think that you will be able to figure out what this should read on your paper. You probably, hopefully, will fit across. This turns out to be, if you punch it all into your calculator carefully, 3.238. Now, to get the standard deviation, we're going to calculate the square root of this. So again, don't round until you get there. Don't punch in 3.28. Use your answer that you already have. Use your calculator to take the square root, or equivalently you can raise it to the 0.5 power. So this is going to be s to get it, we always take the square root of the variance. And you should end up with approximately 1.799. I'm going to write out quite a few more decimal places here just so that you can look at your answer that you got when you did it and verify that you do not have any rounding error. If yours doesn't match mine, it probably means you punched something in when you should have stored it in your calculator. It's a 9. Let's move on. Just a reminder here, the standard deviation is the square root of the variance. I don't want you to forget that. It's very, very important. Now, what about when we have grouped data? We know we can find the mean for this, and it should not be surprising that we can also find the variance and the standard deviation for it. It's going to be the same idea, except that we are going to assume our data points are at the midpoint. And so we're going to use the midpoints to subtract the mean, and then we're going to each time have to multiply by the frequency. I've only put the sample version here, the sample variance with the denominator of n-1, because you very rarely will have grouped data when you're talking about an entire population. Now from here, do we really need a new separate formula for the standard deviation? No, we just have to remember that once we find the variance, we take its square root to get the standard deviation. I've also given you an equivalent formula here, which you can also use. I'm not going to do it that way because I think it's a little less intuitive and doesn't look quite so much like the ungrouped data formula, which we already know. So we're going to go with this. Let's do this example. Okay, we are going to put on the left edge, or whichever side you like, of your table, we're going to put a column for midpoints. These are going to be the xi's in the formula that we saw a moment ago. And what they're going to be is they're going to be halfway through the interval. So if you look at the very first interval, you can see that it is 5 units across, and therefore our midpoint should be 2.5 units from either side. Alternatively, you can average the left edge, which is negative 0.5, and the right edge, which is positive 4.5, and divide by 2, which will give you 2. If we do the same thing for the next one, if we take the 4.5 and add the 9.5, we're averaging them to get the number that's halfway in between. That would be 14 over 2, so 7. And halfway in between 9.5 and 14.5 will be 12. Notice if all of my intervals are the same width, all my midpoints will be the same distance apart. Here all my intervals are 5 units wide, therefore all my midpoints will be 5 units apart. So we can figure out the pattern and then not have to do so much calculation. 17, notice that's 2.5 units from each edge of the interval. 22, 27, and they are going up by 5 each time. 32. This is what you should get for your midpoints. So now first we find the mean, which we're going to call x bar. Remember, what we're going to do is we're going to assume each of our data points is at the midpoint, and then we're going to multiply by the frequency, which is the number of them that we have. So we have 7 measurements at the midpoint 2. We have 53 measurements at the midpoint 7. We have 22 located at 12. And we keep going like this. how many are we going to divide by? Think carefully on this one. How many measurements do we have? We have a lot more than just the number of frequency classes. If you're tempted to count the frequency classes, 1, 2, 3, 4, 5, 6, 7, realize that doesn't tell you how many data points you have. These frequencies tell you how many are in each of those. So to get the number of measurements, we're going to have to add the frequencies. Let me squeeze this in right below the table. 53 and 6. Should get 103 of these. And so what are we going to put in our denominator? 103. For the mean, we do it exactly the same way. We add our measurements, we divide by the number that we have. The mean is the same, whether it's a population or a sample. It's the same thing that you did when you first learned about how to average numbers. So you should end up with about 10.59. Be sure you store this in your calculator. We do not want to round things until we get to the very end and we have our variance and our standard deviation. So now we're going to do the variance, which we call S squared, remember. Now here, our denominator, instead of being 103, it's going to be 103 minus 1. Make sure you remember to subtract 1 from your denominator when you are talking about a sample. And if you notice in the description of this data, it said that we have some randomly selected stocks. That means we do not have all of them. We have a sample of stocks. So we know that we have 7 measurements in the first category. We're going to assume they are all at 2. Therefore, we will take 2 and subtract the mean, which would be about 10.59. Then we're going to square that. In other words, we subtract from the midpoint, we square it, and then we multiply by 7 because we have 7 measurements. And we do the same thing for the next one. Next time we have 53 measurements, so we're going to take the midpoint, which is where we're assuming our data points are, subtract our mean, and square. And continue just like that. Keep in mind, whenever I'm writing 10.59, I'm not typing that into my calculator. I'm punching in the stored value when I do that. You should end up with approximately, again, we're not writing it down. We're not rounding it until the end. I'm just writing this down so that you can check your calculations. You should end up with about 41.87 for your variance. Now, to get your standard deviation, what do we do? It's always the square root of the variance. And we're going to call it S. So it's going to be the square root of our variance. So that's going to be about the square root of 41.87. So take whatever answer you already have in your calculator, take the square root. You should end up with about 6.47. So just to kind of remind us of our notation here, our mean we represented by x bar, our variance was s squared, and our standard deviation s. And that's in the units of the original problem. And so if you look, ask yourself if 10.59 is a reasonable median stock price on here. Well, it looks like you have a whole bunch of them clustered between 4.5 and 9.5, and then some more between 9.5 and 14.5. That certainly seems reasonable. And the 6.47 would be, in a very informal sense, the average distance or deviation from the mean. And I think our 6.47 seems reasonable for that too. I sure hope this helps you figure out how to do mean and standard deviation, especially for that grouped data, which may be new to you.